Okay, a couple announcements. We have exam 4 scheduled for Wednesday. We'll have to see if that happens or not, depending on how much we get through today. So now we're moving into ionic mechanisms, and that's the movement of 2 electrons. So under ionic mechanisms, there's substitution and elimination. Elimination is module 5. And for substitution, what we have remaining is SN2 and SN1. So they're substitution overall, but they're different mechanisms, and we just have to see how much we get through. I'll sort of know better by the end of this lecture about whether the exam's going to be Wednesday or if we need next Monday's lecture as well. The module 5 material on elimination is fairly short to begin with, so it won't really matter that much if it gets chopped down by 1 lecture. Including today, we have 6 lectures left, and then you have your final exam on Wednesday, May 7th. I believe that's the correct time, 10:45 to 12:35. So the university gives you an allotted 2.5 hours or something like that, but the final is the ACS standardized exam. So only get 110 minutes for that, unless you have an approved accommodation. And so that exam is the only one that you have to be here to take in person. It's a 70-question multiple choice exam. Please read the syllabus about the policies related to that. Basically, you have to be here to take it. You can go into the final with a letter grade of an A, and the final exam will not impact your letter grade, but you still have to take it. So my stick is, if you don't take it, I'm going to assign your grade as an I, no matter what you go into the final with. But you do have to take it. And the reason for that is it's part of our reporting requirements for the degree in chemistry and biochemistry. So most of you are not chem biochem majors, but we still have to report that data. Any questions before we get started? So as I said, we're moving into ionic mechanisms now. So 2 electrons are moved, and we're going to use sort of the normal looking arrow that has that double arrowhead. Remember, for radical reactions, a single electron is moving, and we call that the fishhook arrow. There are 2 types of ionic reactions. What we're going to finish up module 4 is called substitution. And then module 5 is elimination. The starting materials for either substitution or elimination are alkyl halides. And again, in terms of my teaching philosophy for this course, why I sort of don't follow the chapter order in many textbooks is that I want to introduce hydrocarbons first. So molecules that are nonpolar, they're just CC or CH bonds. We get those from petroleum or plant sources. And then from that, we're functionalizing. So we're increasing the oxidation state of a carbon to add a halogen. And the halogen, as we see, is a good leaving group. So we're going to introduce some new terms today. And once the halogen is in there, we can substitute it for any functional group you've learned in module 1 and 2. So now is the point where we're going to coalesce everything from these prior modules, and we need to always be thinking about functional group names, nomenclature, carbon uniqueness, proton uniqueness, and now what are the reactivities of those functional groups. So we just saw how to transform an alkane carbon H bond to make an alkyl halide, so Rx, specifically where we were dealing with chlorine and bromine, because the fluorine and iodine do not participate well in the free radical chain mechanism. So what we're going to do now in terms of, say, a general reaction, say we have that alkyl halide, Rx, we're going to treat it with some group, Y, that has 2 electrons, and then we're going to substitute it. So it's substitution. The first reaction is called SN2, so substitution, nucleophilic, and the 2 stands for bimolecular. The reaction shown is sodium hydroxide plus methyl bromide going to methanol plus sodium bromide. All of what I say on this slide will be explained in subsequent slides, but I want to introduce some nomenclature now. You can see that we have 2 starting materials. That's where this number 2 comes from. Organic mechanisms are typically abbreviated like this, some short abbreviation. So 2 stands for bimolecular. That means in the rate determining step, the concentration of both reagents will affect the rate. So the methyl bromide is what's called an electrophile. The sodium hydroxide is called a nucleophile. So in mechanisms, there's always a nucleophile and electrophile. And those terms fall under the Lewis acid-base definitions. So remember we learned about the different theories, so Arrhenius, Bronsted, Lowry, Lewis. So for all mechanisms, we're now sort of considering the Lewis definition of things. A nucleophile is an electron pair donor, and an electrophile is an electron pair acceptor. So the Lewis definition, the acceptor, we would say that's an acid, and the donor is a base. Now, what I want to be very transparent and clear on, when I say acid-base, we're not talking about a proton moving anymore. So proton movement really is better described as Bronsted-Lowry definition. Nucleophile, electrophile, we're talking about electron movement, and that's the Lewis definition. What you'll notice here for methyl bromide, see the bromine atom in the starting material? In the product, it has been substituted for hydroxyl. Now, overall, think about the module 2 when we learned about spectroscopy. So with alkyl halides, we saw that mass spec gives some signatures for the different isotopes. Chlorine has 3-to-1 of the parent. Bromine has 1-to-1 of the parent. Now what about for methanol? The best method to determine that a hydroxyl group is there is to use IR, that's the broad OH stretch. So as we introduce these new functional groups through substitution, please always try to think about what's the best method, spectroscopic method, to use to validate that the substitution has occurred. Any questions so far? So let's consider a CX bond. So I'll just draw out that bromine. Just the CX bond itself, nothing else attached to the C. That can be whatever. So which of the following answers best describes the nature of that bond? So B, it's a polarized bond. Bromine has 3 lone pairs of electrons, so we can say it's delta minus. Carbon is therefore delta plus. And if we convert that into a bond dipole, we would draw a bond dipole like that. And so why is that important? Why is it different from sort of a CH bond? So notice in a CH bond, we know hydrogen only forms 1 bond, so it has no lone pairs. And the electronegativity difference is less than 0.5. So that was our sort of Rubicon about determining polar versus nonpolar. So this is nonpolar. So the bromine atom is what we are substituting. So when it's substituted, it has to leave. So we have to cleave that carbon-bromine bond. The electrons in that bond leave with the bromine. So 2 electrons, notice the delta negative. What that's telling you is when we draw an arrow, those electrons can be accepted by the bromine. The bromine's sufficiently electronegative that it can take those electrons and be happy. So bimolecular nucleophilic substitution reaction. So we call this just SN2. In the SN2 reaction, the nucleophile attacks the electrophile. And so I'll highlight that with the arrows down below. So I'll do that in green. The sodium hydroxide has 3 lone pairs. Overall, the oxygen's formally negative. That arrow is indicating the movement of 1 lone pair or 2 electrons. Notice the arrow starts at the lone pair, and it's pointing to that delta positive carbon. So the arrowhead where the electrons are going are pointing to something electropositive. So we're making an OC bond, and you already know from the Lewis dot rules that carbon can only form 4 bonds, so you have to break an existing bond. So we form O to C, we have to break C to Br. So now those electrons I'll highlight in blue, they move on to the bromine. And so bromine is called the leaving group. And then what you'll notice, we form an inorganic byproduct sodium bromide that may precipitate out of the reaction. As you know, those arrows, we've pushed them. The arrows show the trajectory or movement, but it also happens in a very specific way. The nucleophile attacks the carbon that's bearing the leaving group at a trajectory of 180 degrees away from the leaving group. And so we'll explain that on the next couple slides. So the electrons, they don't take a random path. It's very guided, and the reason for that is the molecular orbitals involved. So we know that the line here indicates a carbon-bromine sigma bond. So a sigma bond is 2 electrons, where basically the carbon is supplying an orbital, bromine supplies an orbital, they form a sigma bond. So carbon and bromine both supply an orbital. That's 2. One of them is called the sigma orbital. The other orbital that forms is called sigma star. That's higher in energy and it's unoccupied. So we'll use these terms. So sigma, that's an occupied orbital. You can see the line, that's 2 electrons. But then probably what we haven't talked so much about, but still exists, is the sigma star. It's an unoccupied orbital. So see the directionality of the carbon-bromine bond? 180 degrees to that, sort of behind the leaving group, resides the sigma star. And I'll draw that in sort of blue. So the sigma star has a big lobe and then a little tiny lobe. Sigma star, we're going to say, is unoccupied. Do I have 2 P's or 1? I think just 1. No, that word doesn't look right to me, but it's unoccupied. It exists, but it's not filled. The lone pair from oxygen is going to fill it. That forms the new bond. The existing bond then breaks. In terms of nomenclature, how your book will describe this, the flow of the arrows down here, N means a lone pair from oxygen is flowing into the sigma star of the carbon-bromine bond. And so we've seen how to push those arrows, and now the trajectory is important. Because as we'll see, this carbon, or of the starting material, now it has 1, 2, 3 hydrogens in a bromine. But if you can imagine, instead of having 3 equivalent hydrogens, if those were 3 different groups, and that was then a stereocenter, notice how all of these hydrogens, if we draw a line, they form sort of like a triangle on this side. When the nucleophile attacks, look where the hydrogens end up. They're now sort of on the right side. So not only do we account for electrons, but we have to account for stereochemistry. And in the SN2 mechanism, there's an inversion of the carbon. So we talked about CIP nomenclature with R and S. Depending on what the carbon bearing the leaving group, if it's a stereocenter or not, the inversion is going to happen, but then we also have to consider, did the R to S or S to R flip? So it says, which of the following alkyl bromides will not react by SN2 mechanism? Which one of these is not like the other? So A, and what's the reason? So the double bonds, so that makes that carbon sp2 hybridized. So really when you're diagnosing a molecule or a set of molecules and you want to determine where a substitution is going to happen, so SN2 can only take place on sp3 hybridized carbons. One way to think about that, if you look at A, see the carbon bearing the bromine? So if that's sigma, and then we drew this sigma star, sort of 180 degrees. Look at where that orbital resides. Directly opposite, you have a carbon atom. And remember, the nucleophile has to reach that sigma star, so it cannot go through an existing carbon atom to get there. There's probably better ways of explaining that, but that's probably the easiest to see with how the electrons flow. So which of the following adequately explains why sp2 and sp hybridized carbons bearing hydrogens do not undergo SN2 reactions? So B as in boy would be the correct response. That sigma star is not accessible to the nucleophile. So in understanding how the term SN2 arises, again, the 2 stands for bimolecular, and that's related to the rate equation. So the overall rate is equal to the rate constant times the concentration of the nucleophile times the concentration of the electrophile. So remember the nomenclature, the square brackets, we're going to use molar concentrations for that. So stated that another way, both the nucleophile and the electrophile have to be present to react. So 2 things have to collide for the reaction to occur. In the energy coordinate, the rate determining step is the energy of activation. So that's when you have your starting materials and then you're going uphill. Whichever hill is the highest to climb, that's the energy of activation. And that determines the overall rate. One way to think about rate is like traffic, so cars moving. So if you've ever traveled on the interstate and you get to like a choke point, say like a bridge, like traffic usually slows down as it approaches a bridge, either because lanes are narrowing down or just because there's this unfamiliar obstacle and people get nervous and they slow down. So that's what we mean by rate, so speed. So as we look at these coordinates, the top or the peak, the highest peak, that's where the transition state occurs. So that's abbreviated TS, or sometimes it'll have that superscript dagger symbol. A transition state, again, is kind of weird. You have to, suspend your normal sort of foundational facts. Things that can happen in the transition state do violate the normal Lewis dot rules. So in the mechanism, when you have a bond forming and a bond breaking, that sort of happens at the same instant in the transition state. So translated to what you know, if you have those 3 hydrogen substituents or whatever, nothing's happening to them, so that's 3. You have a bond forming and a bond breaking. That gives you 5 total substituents around the carbon. And we've said before, carbon's limited to 4. So at the transition state, that's when it's highest energy, because carbon's pretty unhappy. It has a bond forming, a bond breaking, 5 things around it. It's higher in energy. So on the left side of the coordinate here, in our starting well, we have the electrophile bearing the leaving group, the nucleophile supplying electrons. That lone pair attacks the sigma star orbital. At 180 degrees opposite the leaving group. So as it climbs the energy hill, so we're going up in energy, so our delta G value is greater than 0. So we can think of that as, in terms of heat, that would be sort of a plus sign. And then the transition state in the square bracket, you have bond forming, and then you have bond breaking. So how is carbon able to accommodate that? Well, it starts off as sp3. We know that because there's 4 sigma bonds. To accommodate the formation and breaking, the carbon in the transition state actually rehybridizes to sp2. So sp3 here, now it's sp2. And the reason for that is because it has that p orbital where electrons can go into, and then the existing electrons can leave. And so that's, again, going uphill to the very top, and then when we go down, the OC bond is fully formed, the CBr bond is fully broken, and now we're in the product well, and the carbon has gone back to sp3 hybridization. So for this example, where we started with, if we look at the dotted red line in the middle, the starting material well, then the product well, notice that's lower, so overall for the reaction, that would be a negative. Any questions? So I've stated this a couple times before. This is not a math class. We're not doing advanced mathematics here, but I'm showing you these equations so we can understand a little bit about how these signs end up plus or minus when we determine the thermodynamics. In the prior discussion on radicals for bond dissociation energies, we were using enthalpy, so the H term. Overall, for a reaction, including all the factors, we use what's called Gibbs free energy change. And so that's delta G. This little degree sign means standard conditions. So the delta G is more accurate overall for a reaction because you're considering more than just the energetics of bond making and breaking. So delta G is equal to negative 2.303 times the ideal gas constant times temperature times the log of the equilibrium constant. Stated another way, that's equal to the change in enthalpy minus the product of the temperature times the change in entropy. So H was enthalpy, T was temperature, and then S is entropy. Entropy is a kind of weird concept to understand. It relates, the word that I think about is to chaos. So think about your dorm room when you clean it. It's nice and tidy. Now, how does it look after 3 days? Is it still nice and tidy, or is the chaos increased? So entropy is a measure of that, kind of related to mechanisms. You can think of it as the number of things being produced. So overall, we use slightly different terms for Gibbs free energy. If the value is less than 0, so if it's negative, we use the term exergonic. So like exothermic, that's specifically tied to enthalpy. So if delta G is greater than 0, so if it's positive, that's endergonic. So enthalpy would use endothermic. So just keep in mind that the different terms in that equation have different ways of describing the overall process. So in terms of the kinetics, because of that 2 in the mechanism, we say that the SN2 follows second order kinetics using that rate equation. So overall, the units for the equation are moles per liter second. Therefore, the K has units of liter per mole second. And then the square brackets we said was molar, that's moles per liter. I'm not going to dive too much into having you shove numbers in that equation or figure units out, but you do need to have sort of a qualitative way of thinking about, when you change these concentrations, how does that affect the overall rate? So for example, if you double these concentrations, what happens to the rate? The rate has to increase because you're putting more of that stuff in. So that would be a quantitative way, but for organic chemistry, a more qualitative way of determining rate is the classification of the alkyl halide. So the alkyl halide is the electrophile, and really based on the way the electrons flow and their movement, you want a carbon atom that's very unhindered. So a methyl, say methyl chloride, methyl bromide, that's going to react much faster than, say, ethyl bromide, or say 2-methyl propane, or say a tertiary. So that would be a methyl bromide. That would react faster than ethyl bromide. Which would react faster than 2-bromopropane. And then that means much, much greater than. So if you have a carbon that has 3 other carbon substituents, so a tertiary substrate, those do not react. So those do not react by SN2. So you need to be able to classify the carbon bearing the halogen, what is methyl, primary, secondary, tertiary, and then if you have a competition, which one reacts the fastest. So I want to put a caveat here. This is the trend for SN2. Tertiaries do not react by SN2. That said, they still undergo substitution. The substitution, though, occurs by a different mechanism. That's called SN1. So unimolecular substitution. So this gets to the thought process here of the importance of diagnosing the reaction conditions so that you can determine the mechanism by which it's occurring. So here's a slide that hopefully illustrates why that trend is. So in the first column here, you see the class, so methyl, primary, secondary, tertiary. An example of the haloalkane. Then in the third column, it's showing you the structure, so the carbon bearing the bromine, what's bonded to that carbon. The fourth column, you have to imagine putting your eyeball directly behind the carbon leaving group bond. And then if you did that, that blue ball is showing you sort of the sigma star orbital. And then next to that is a space filling model. So you see in gray, or excuse me, sort of like lighter gray or white, those are the 3 hydrogens, 1, 2, 3. Then this dark gray in the middle. You can imagine that the sigma star orbital is there. The thing you can't see is then the bromine because it's in front of the carbon. As you substitute these hydrogens for carbon groups, so C to CH3, now what you see is that the space where that sigma star is, there's less volume or space available there. So that space here is now decreased because it's occupied by a bigger carbon group. Then when we substitute another methyl group on, we now have 2 in the secondary. That space is now further decreased. And then in the tertiary, it's just that little bit there, you can't even see it. So the lone pair cannot even get into that sigma star to bond. And that helps explain the rate is related to the class of the bromide. And then the last column is showing you sort of secondary being a benchmark rate of 1. A primary will react 50 times faster, and a methyl group 1,000 times faster. The tertiary, the rate is so slow, it's not appreciable, and again, it happens through a different mechanism. There's one other group that's pretty common we have to be aware of. If you look at the structure drawn, we would classify this as a primary bromide. And now if I use this term alpha, to designate the carbon bearing the leaving group. And then I go out one more carbon to the beta carbon. Notice that that has 3 carbons attached to it. When you look at the Newman projection, sort of again from where the sigma star would be, and then the space filling model, you can no longer see that sigma star orbital. So this type of primary halide is called neopentyl. So pentyl because there's 5, neo because whatever, I'm not sure. But just beware when, if you have a primary, go out to the beta carbon and see how it's substituted, if that's going to affect the rate. Any questions? So for SN2, we're really looking at halide / leaving group classification. So methyl reacts greater than primary, reacts greater than secondary, and tertiaries do not react. Again, keep in mind, these are all carbons that are sp3 hybridized. As we increase the steric bulk, so around the alpha carbon, that slows the rate of reaction. So which of the following alkyl halides will react fastest via SN2 mechanism? So you have these names. The best thing to do would be convert them into structures and then classify them. So 2-bromopropane, we would say that's a secondary. 2-iodo, 2-methyl propane, say that's tertiary. One bromo, 2-methyl propane, that's primary. And then 1-bromobutane, that's primary. So tertiary is going to be the slowest. Then you have this secondary, but now you have 2 primaries. So which of the 2 primaries would react fastest? So the answer would be D. Again, because when we look at that beta carbon, we can see for answer C, it has more substitution, so it's bulkier. It's going to have a slower rate than just D. So I think these are the, the same ones. The slowest one will be B. And again, because that's tertiary. So again, that alpha carbon has 3 carbons bonded to it. So sigma star is not accessible. So as we dive a little bit deeper into the mechanism, we're going to look at these individual parts that are important in facilitating it. So what about the nature of the halogen leaving group? What makes a good leaving group? We know from the halogen group there's fluorine, chlorine, bromine, and iodine. So in our haloalkanes, the thing in the box is the leaving group. Then notice for the comparison, we're just keeping methyl the same for all of them. Column 2 is showing you the bond length. So notice that the bond length increases going down the group. So if your carbon atom is sort of static at one point, the carbon-fluorine bond is the shortest, carbon-iodine is the longest. And one of the ways of sort of rationalizing that why does the bond length get longer? Well, as you go down that group, you're adding more and more electrons, so that atom itself gets bigger. The carbon atom, again, it's staying a constant size, but the size of the atom it's bonded to is changing. So when you get to iodine, it's a really big atom, and so you have a bigger bond length. The way we sort of quantify this is according to pKa. So when the leaving group leaves, notice that it gets a negative charge. So it becomes halogen minus. If we consider the acid, so the conjugate acid of that leaving group, so the mineral acid there, then we go back to that trusty pKa table, look up the pKa's. Notice that the pKa increases as you go down the group. And really the line that we want to pay attention to is where the sign inverts. So between fluorine and chlorine. So notice fluorine is a positive 3.2. Everything else is less than 0. So what makes a good leaving group? It's if its conjugate acid has a pKa less than 0, that's going to be a good leaving group. So in terms of the ability of leaving groups, iodine's the best, followed by chlorine, followed by bromine, and fluorine is not a good leaving group. That may seem weird because when fluorine leaves, it becomes F-, and we know that fluorine's the most electronegative, but these other factors outweigh that. What about if we started with methanol? And we wanted to substitute the alcohol of methanol for bromine. Well, it turns out that you can't do that. And the reason is based in the pKa argument. So the leaving group would be hydroxide. The conjugate acid of hydroxide is water. The pKa of water is 14. So notice that's not less than 0. So OH is a terrible leaving group. But in organic chemistry, it's pretty easy to make alcohols. And once you make them, say you want to substitute them, so how can we do it? If we pay attention to this H of the alcohol, we can transform that into something else. And then overall, we make that a good leaving group. So if we react an alcohol with a molecule called a sulfonyl chloride in the presence of a base, triethylamine, so that's a nitrogen with 3 ethyl groups on it. The H gets removed, it gets replaced really by all of this stuff. And so the byproduct of that is HCl. So that's an acid. That's why we use the triethylamine as the base to neutralize that. So that's a byproduct salt. So N, N is plus, Cl minus, or written another way. So once you have a sulfonate ester, that's now a good leaving group. You can do substitutions on it. So why is it a good leaving group? So in this reaction, say we have sodium bromide. So NaBr, the Br is negatively charged, so that's a nucleophile. We have that polarity difference of the electrophile between carbon and oxygen. So the nucleophile can attack the carbon. We can now break the CO bond. That does the substitution to generate bromomethane, but then look at the byproduct. So that's called a metal, so sodium, and then sulfonate. So we've seen sulfuric acid before. We know that's a strong acid. The difference between the sulfonate and sulfuric acid, we don't have that second OH group. It's replaced by an R. It attenuates the acidity a little bit, but the conjugate acid of that, when we look at the pKa values, we see that those are very strong acids. So in our table, we've activated the hydroxyl group by removing the H, putting on a sulfonyl group. Then we get this sulfonate leaving group. And then we look at the conjugate acids, we see they're all less than 0. So that means they're good leaving groups. Any questions on that so far? So the next factor that we're going to look at is the solvent. So when we think of solvent, we think of a liquid. And if you have the two starting materials, the nucleophile, the electrophile, why do we need another chemical in there? Why do we need a solvent, a liquid? So one reason it helps dissolve the starting materials. If your nucleophile and electrophile are both solids, like they're not really going to react, right? Because you can't get two solids to mix properly. You know, if you take like peanut M&Ms and just chocolate M&Ms, I mean, it's just two solids. Just, you need things to be in solution so that the collisions can happen. So solvent helps dissolve. It also serves as a heat sink or a heat source. So by source, I mean you can heat the reaction. That's like when you boil your water on the stove, you're adding heat into the reaction. Because solvent is typically there in a huge excess, that solvent can take the heat, transfer it to the molecules, and help with the reaction. Or if the reaction itself is exothermic and it generates a lot of heat, the solvent molecules can take the heat from that reaction and dissipate it. So it's used for dissolving and controlling temperature. So notice the structures of the solvent shown. These are classified as polar. So they have polar functional groups, and they're also classified as aprotic. So aprotic means without an active hydrogen. So without, say, OH or NH. So the common solvents are acetone, that's a ketone, hexamethylphosphortriamide, acetonitrile, that's a nitrile, dimethylformamide, that's an amide, and dimethyl sulfoxide, that's a sulfoxide. So how are they polar? So you have a carbonyl group here for the ketone, so delta minus, delta plus, that imparts polarity. HMPT, you have delta plus, delta minus of that PO double bond. The nitrile, nitrogen's negative, carbon's positive. DMF, same thing for the carbonyl. And then the sulfoxide is just an SO double bond, so delta plus, oxygen, delta minus. So notice some of these have sort of lower boiling points, others are above 100, and that's what we mean by adding heat. You can heat that up. That helps lower the energy of activation. And then more importantly is the last column called dielectric constant. So DMSO has the highest dielectric constant of 49 and acetone's 21. That plays into how the solvent molecules interact not only with your starting materials but also the transition state. In the lab, if you were to do one of these reactions, acetone is probably the easiest to work with because it has the lowest boiling point, which means you can get rid of it the easiest. But sometimes it's not polar enough. So you have to go up to these solvents with higher boiling points like DMF and DMSO. These can be kind of a pain to get rid of because of the boiling point. But due to their high dielectric constants, they may be the only ones that facilitate the mechanism. So why do we need these polar aprotic solvents? So again, polar, there's some change in electronegativity. Aprotic, They do not have OH or NH bonds. One of the reasons is nucleophiles typically have this form where you have a metal cation and then your nucleophilic component that has the electron pair that's donated is then negative. As shown in the little picture here, the metal cation can get solvated by solvent molecules through non-covalent or electrostatic interactions. And so what this picture shows very crappily, so here you have a salt, right? Cation, anion, that's an ionic bond. They're close together. When you put it in the solvent crowds around the M. That leaves the nucleophile more exposed. And why is that important? Because again, it has that lone pair that has to participate. So if you're taking away that metal cation, the nucleophile lone pair is free to do its business. Any questions? So just to recap that, your typical nucleophiles, when they're in this form, metal cation, nucleophilic anion, the nucleophile is the Lewis base. So supplies electrons for the reaction. You add the solvent, it helps expose those electrons so that you can get the reaction to proceed. So what I'll say now is we're talking about SN2. We have these different factors that facilitate it. When we get to these other substrates that are tertiary, a lot of these trends are just the opposite. So for an SN1 reaction, we use polar protic solvents. And so it has a similar logic as to why. But a protic solvent in SN2, it's basically going to hinder the reactivity of the nucleophile. So factors that affect nucleophilicity. So nucleophilicity, so ability to donate lone pair of electrons. The blue arrow here, that's your electronegativity trend, which we're used to seeing. So all roads point towards fluorine as being the most electronegative. The red arrow is the opposite. That's nucleophilicity. That's the ability of that atom to donate those electrons and be a better nucleophile. So when comparing a negatively charged nucleophile to say its conjugate acid, so if hydroxide versus water, so we'll say negative versus neutral. the negatively charged one will react faster because it has that lone pair exposed. That's why it's bearing the negative charge. So hydroxide is a better nucleophile than water. And then in terms of moving horizontally, comparing different elements but in the same period, nucleophilic strength decreases moving left to right. So NH2 minus is stronger than OH minus, which is stronger than F minus. And again, that's explained by the blue electronegativity trend and the red nucleophilicity trend. So here's a meme for you. Is that from The Incredibles, I think, if I remember right? So nucleophilic attack is a reaction. The nuke attack is atomic warfare, nuclear warfare. Okay, so let's do some organic chemistry Mad Libs here. In an SN2 reaction, the blank supplies a lone pair of electrons to attack the blank at a trajectory of blank degrees to the blank. So in terms of Roman numeral 1 there, the nucleophile supplies the lone pair of electrons, so we can eliminate A and B to attack the electrophile, so we can eliminate D at a trajectory of 180 degrees to the leaving group. So C is the correct response. So that's a verbal way of describing the mechanism, but then you should also be thinking about that in terms of drawing the curved arrows. So in our last 6 or 7 minutes here, now that we know the factors affecting the SN2 reaction, what are the different functional groups we can introduce? And so this is where we need to remember all those spectroscopic techniques. So the way these slides are organized, we're going to march across the periodic table. We'll look at carbon first, then nitrogen, then oxygen nucleophiles. So carbon nucleophiles bearing a negative charge are called carbon anions or carbanions. And when we talk about them in terms of nucleophiles, it's a negatively charged carbon attacking another carbon. So they are not acting as proton transfer agents. So our common starting electrophile here is going to be methyl bromide. And then if we use potassium cyanide, so K plus Cn minus as the nucleophile, again, that has to attack opposite the carbon-bromine bond. We break that bond. The bromine has been substituted now for the nitrile. So remember, once you get a nitrile in there, that triple bond is in region 2, 2400 to 2200 is a sharp singlet. You can also make alkynes. So notice what we're starting with. sodium propionolide. So that is generated by the treatment of propine with sodium hydride. So that's an acid-base reaction. That generates this negatively charged carbon that can attack, expel off the bromide. And we've started with an alkyne, and we've ended up with a higher order alkyne. So we added a carbon atom. Again, for each of these reactions, notice I've just given some general conditions. So DMF, 120 degrees, DMSO, 60 degrees. A lot of these SN2 reactions do require some heat. You know, unless you have a really strong nucleophile-electrophile pair, a lot of them don't really take place at room temperature, which is 25 degrees, again, in Celsius. You remember the Arrhenius equation? So you can double the reaction rate for every how many degree change? A 10-degree change, it doubles the reaction rate. So if you get nothing at room temperature, so 25, 35, 45, 55, you increase by 30 degrees, you should start seeing some action then. We'll end on this slide, nitrogen nucleophiles. Notice this nucleophile ammonia, it's neutral. We know ammonia has a lone pair, right? In theory, on paper, you could take ammonia, have it attack that carbon, and now you've made a primary amine. So methylamine. Any Breaking Bad fans in the audience? So methylamine, it's really expensive to buy, and it's restricted by the DEA because it's used to make methamphetamine. This would be a terrible way to make it, and the reason is because notice the product that you're producing. It's still an amine, it has a lone pair. So even though you're forming this as a product, it can still behave as a nucleophile. And it will. So it'll undergo a second alkylation or substitution. So it'll go from the primary to form the secondary. That still has a lone pair. That will form the tertiary. That still has a lone pair. And now it'll form a quaternary ammonium salt. So ammonia as itself is a bad nucleophile unless the conditions are really well controlled. So that's going to lead us into this question of how can we get nitrogen into a molecule without having this issue? And basically, we have to deal with these hydrogens. So we have to figure out something to do with that. So we end up with nitrogen that can't over-alkylate through multiple SN2s. And that's what we'll pick up on Wednesday. And so based on where we're at now, we'll definitely move the exam to next week so that we can finish off SN2 and SN1.